Good morning, colleagues. As you have said, my name is Rasel Omiteki. On a personal note, before I continue, Professor Kara, when he was still Dr. Kara, he inspired me. They actually came to Africa with Dr. Mohammed at the time. And today I'm here. I think it's because of them. Professor Kara has been in the staff of the school and previously the Department of Mathematics over 30 years as a teacher, researcher, and administrator. Professor Kara has published widely with collaborators locally and abroad. His work is highly cited with satisfactory Scopus H index. He has supervised a number of MSc and PhD students, as well as co-supervised a number of other PhD and MSc student completion. Professor Kara has taught a number of courses with great success at all levels, from first year through to master's level. He is presently the head of School of Mathematics. Over to you.
Thank you, Joe. Joe always reminds us of that trip to what was then University of Botswana University. It was an interesting trip because it included Noether eventually, who's one of the founders of some of these new results and so on. So you remember that time. And anyway, so thank you, Joe. In some senses, I'm glad that there are very few people particularly working in this area. It makes it easy for me to speak more about the area rather than specific results. Because when you get into the technicality and you've got some experts, you ask the question, do you always get nervous speaking? That's when I get nervous. When there's in the audience people who know, because you can't then work around and think about the question. So when they know, you got to know what to say. So I must say, but there are quite a few people. I then be careful of David Mason being on. Okay, so the title looks slightly different from what you would have seen in the lift or advertised in your email. I just sort of abbreviated the title, but essentially it's about some of the methods involved in constructing conservation laws, and once we have conservation laws, what are the kind of things we can do about it? So although I give a summary of what the talk is going to be, much of the first part of the talk is about the history. History meaning the kind of results that were established until very recently, from say just over 100 years ago. Towards the end, it will become a bit technical, dealing with recent results. I will speak about them for the benefit of those people working in this area. Okay, so in a sense, there's a summary of what I'm going to speak about. So the first point there, the bullet point there is about symmetries and conservation laws, just to speak about the kind of mathematical results that exist already in the area and where it all started. Maybe some of the implications in physics and even engineering for that matter. Over time, we expanded some of these results to accommodate what we call approximate symmetries, dealing with differential equations that involve a small parameter. So you have your differential equation, your standard heat equation, or your KdV equation, and sometimes physically you want to perturb that by a small amount and see what you get. Okay? So for example, the kind of thing you do is when you have a wave equation, which is a complete wave, right? And then you introduce a small parameter that will force the wave to decay. So equations of that type we sometimes refer to as differential equations involving a small parameter of a certain order. So if epsilon represents your order, maybe if you keep it to order 1, so you got epsilon raised just up to 1. And there are some nice results in this particular area dealing with equations of that type. There's lots of work still to be done. Probably it was ignored for perturbations or the approximate part being of higher order. The notion of partial Lagrangians, I'll speak about and I'll say what that means, because it's still very disturbing to many people who are particularly from physics, that how can you speak about a partial Lagrangian? But I'll say what we mean by that. And then I want to look at some of the more recent results in this area. Okay, so what is summarized here in the next 3 or 4 slides essentially is about the history of this area. I'll speak about it and then just skim through the slides itself. So all of you have come across in your physics courses somewhere along the line the notion of conservation laws. So we know about conservation of momentum and energy and angular momentum, etc. Right? But for a long time, the association or the link between the established notions of conservation laws and the invariance of your system was not quite known. Right? There were ideas, there was hunches that people had about the conservation of, say, angular momentum. What is it related to in terms of your symmetry, in terms of the invariance of the system? And one of the ones that was common, it was well known in physics, is that you've got your conservation of energy, and conservation of energy arises in a number of places. But what was it associated with? So there were ideas that the conservation of energy particularly had somehow linked to the invariance of a system under time translation. So if a system doesn't vary over time, that's built into your differential equation. The chances are, the idea was that it was linked to the notion of conservation of energy. But there was no established result up to that point as yet. And it took Felix Klein then to convince Emmy Noether. Emmy Noether, remember, was an algebraist. I mean, we know that Noetherian rings and so on. Same Emmy Noether. So she was convinced, or she was sort of lured into this study of differential geometry, and under the advice of Felix Klein, she worked on this notion of conservation laws and symmetries and invariance and invariance of systems and so on. And what she proved was an amazing result in 1918. She proved, in fact, that not only was energy linked to invariance in time, she generalized the result into what's now known as Noether's theorem. So Noether's theorem is actually a theorem, although she was famous in algebra, a famous theorem is named after in differential geometry. And it goes like this. It says that if a system experiences invariance, it is linked to some sort of conservation law. So, but I should put a proviso here. It was specifically for differential equations that were derived from a variational principle. Now, there's a whole thing about calculus of variations and so on. I won't go into the definition of what variational differential equations are. But what it says is the following, that if your differential equation is derivable from a variational principle, there's a Lagrangian. And from that Lagrangian, if you can construct symmetries, if you can study the invariance by the Lagrangian, then each symmetry of coming from that Lagrangian is linked to a conservation law. And one of them was the symmetry or representing invariance in time. So if your system is invariant under time translation, for example, in a variational system, then it experiences conservation of energy, physical. And not only that, she developed a formula where you could actually construct the conservation law. So for the first time, you could construct conservation laws by formula. But just remember, the system depended on the knowledge and the construction of a Lagrangian. Now, many physical systems, like in physics and so on, the Lagrangians may be known. You could find the Lagrangian. Or the system was constructed based on a Lagrangian coming from optimization and so on. The trouble is, many physical differential equations, the ones for particularly partial differential equations, your evolution type equations, heat equation, well-known equation, KdV representing shallow wave studies, Berger's equation representing shock waves and so on. These are all evolution type equations, but they are not derivable from variation principles. So there's no Lagrangian. So if you wanted to study the conservation laws of those kind of systems, you had to find alternative ways, alternate to Noether's theorem. Noether's theorem was fantastic. It's just that you needed a Lagrangian. So you had to, if the system has a Lagrangian, so you can sometimes test whether it's variational. Not only should you know whether it exists, you could actually construct it, because the formula in Noether's theorem requires that you know what the Lagrangian is, and then you can construct the conservation. Like I said, the wave equations and so on, they work well. But when you got these evolution type equations, and many physical systems, you find mathematical physics, there's a whole class of diffusion type equations, for which there is no Lagrangian. So there was a genuine need to find standard, some sort of constructive way to construct these conservation rules. And of course, the work began. And so this is just saying that the popularity of Noether's theorem is exactly that you have this formula. Now, as a result, there's been lots of work done by many people over the last, what, maybe 20, 30, maybe even 40 years to find ways of constructing Lagrangians, constructing conservation laws. Now, we have a mathematical definition of a conservation law. It's all built into the mathematics. So if you took the definition of a conservation law and then just did an analysis on that mathematical definition, you open your equation up, do an analysis, and so on, you can then find conservation laws. No Lagrangians needed, you're just using the definition. I'm not going to get too much into the definition. Let me find the formula that perhaps gives us the definition. Okay, so the conservation law, let me just say, rather than write it down. Your conservation law essentially involves taking your system and writing it in conserved form. So if you succeed in writing your system in conserved form, then the kind of functions that come out of there are automatically your conservation law. So you can mess around with the definition of you've got your system of equations, you mess around with it, and you can then conclude this is your conserved vector if it's a partial differential equation, or this is your first integral if it's an ordinary differential equation. It's a matter of just opening up your definition. But that doesn't work always well because it's endless calculations. You like to find some sort of thing that is very close to or mimics Noether's theorem. Can you find a formula to construct conservation, right? And in that spirit, right, you would want to include the notion of symmetry, because it's always felt that conservation laws, or the notion of conservation, is linked to the notion of invariance. Sounds even similar. You've got something that's conserved and something that is invariant, right? So can we take the well-known symmetries of the equation? And for those that are not familiar with this field, just think about symmetries of your system to be some way of determining invariance of the system. So your system is invariant, it's not changing. You study that. So you look at the invariance, and then you look at your maybe conservation laws, because there's a mathematical definition. And if you can somehow develop a formula for that link, then perhaps you have some sort of formulated way, very close to Noether's theorem in constructing conservation. And that's what was done. Okay, so remember, now we're moving away from the notion of variational principles or having any knowledge of a Lagrangian. If you get a Lagrangian, life's easy. You got Noether's theorem. Mostly you won't have that. That's when you have the uneasy life. And we try to make that life easy. So it turns out that sometime in, when you say these things about you came to us, it makes me feel like I'm old. So we had this result from, and I just thought of it the other day, it's now 20 years, this result. It's 20 years, okay? So Faisal Mohammed and I worked on this result, and using the methods of differential forms, and we had to relearn the whole notion of how to construct or use differential forms and so on. It's like learning something new. That's interesting. And it turned out that you use this powerful method of differential forms where you try to look at your differential equation, set up a conservation law equation, and instead of from that construct your conservation law, you ask yourself, when is your conserved system, the thing that possibly involves a conservation law, when does such a system experience invariance? In other words, can you now link your conserved form to the notion of symmetry, irrespective of a Lagrangian? Okay? And after working for a long time on it, we developed this result that says the following. Now think of, I can use my pen. So this X here is your symmetry, the thing that represents the invariance of the system. That's calculated or constructed or determined independent of conservation laws, so nothing to do with conservation laws. I give you a system of equations. I say, find the symmetries. Give me the invariance. That's what we construct. It's essentially a vector field that represents the invariance of the system. And then suppose we have in some way constructed a conserved vector. I say conserved vector, I refer to PDEs. First integral is the equivalent notion for ODEs. And see under what circumstances is there a relationship between the two. So the way to do it was, you first step back. What does this mean for Lagrangian system, Noether's system? And then see if we can move towards finding that for systems beyond the Lagrangian systems. And that was the sort of the way we looked at it. And we found that the equation that needed to be satisfied, or the relationship that needed to be satisfied, is this particular notion, that particular equation. So if that equation is satisfied, it was a long and winding theorem we had to prove. If that particular equation is satisfied, then we know that there's an association, there's a link between your invariance, your symmetry X, and your conserved vector, your conservation law T. Now, some of the consequences of this are the following: that for ODEs, these terms all disappear. That will disappear. Just believe that. Which means that for ODEs, for a system to have a relationship or an association between symmetry, the invariance, and the conservation law, all you need is your symmetry, your vector field on your components of your conserved vector to be equal to 0. What that means is that if you have your differential equation invariant in the symmetry, your conservation law is also invariant under the symmetry. Then you have association. So trust me when I say that that is the equation that defines a relationship between symmetries and conservation. What was the consequence of that? We want to know why. Okay. So mathematically, what is done is to, of course, you take your differential equations. If you know the invariance, you can reduce your differential equations. And all of us know that when you're dealing with finding solutions of differential equations, you're essentially wanting to reduce the order. That's the first thing. When solving a second order ODE, what do? Whatever method you use, you're reducing to first order. And then if you're going to go further, you reduce it to 0 order, which is solution. For PDEs, what are you reducing? You're reducing the number of independent variables. Whatever it is, you are reducing order of some kind. So your invariance, your vector X, vector field X, allows you to reduce the order. Your conserved vector with the symmetry allows you to reduce it even further. So when you can establish a relationship, a connection between invariance and conservation law, you have this added advantage of reducing not once, but twice your system. So if you have, say, a fourth order differential equation, say ODE, you can reduce from fourth right down to second order. If you have a second order ODE, you can reduce right down to a solution. So second order to first order to solution. Yes.
Talk about Karina along those who are not very familiar. When you talk about invariant under what type of transformation? Or is it in absolute terms? Or?
In fact, that is what we say. So you're looking at invariance under a transformation. But the transformation we're dealing with in this particular area are transformations we refer to as one parameter Lie groups of transformation. I know it's a mouthful, but there are particular kind of transformations. These one parameter Lie groups of transformations, which allow you, so if they are there, you are in some way you can show that those transformations can be written as vector fields. And when we deal with these vector fields X, we are exactly talking about that kind of transformation. But this particular one parameter Lie groups of transformation, there's a whole thing about it, whole theory. Essentially transformation, invariant under transformation. Okay, so far as partial differential equations are concerned, we in fact showed, a faithful student, Astri and Petokos did quite a lot of work in showing that in fact you can double reduce partial differential equations quite successfully to get solutions when you've established relationships like that between symmetries and conservation laws, between invariance and conservation laws. But we went further. In the later papers, we showed that in fact you can construct new conservation laws if you have a set of conservation laws by particular relationships, which again depends on this equation 2.1. So that was an added advantage. So that eventually what you can do is establish a basis of all conservation laws and maybe construct all your conservation. So that was one of the methods used to construct conservation laws, relatively recently, I would say, when you had systems which need not depend on a Lagrangian or any variation. So yes, just an example. I think this was an example taken from one of Petokos' papers, where we show that for your KDV, your equation that represents shallow water phenomenon, you take one vector field. So the vector field X essentially represents your invariance. So this is your one parameter Lie group of transformation, say, and this is your conservation law. So here they were found independently. You find your symmetries independently, your vector field X. You find your conserved vectors separately, perhaps you can do that. Or what you can do is say, let's impose the symmetry on the conservation law via that equation 2.1. the thing that establishes the relationship. And if you can solve for the vector field, at least for the conserved vector T1, T2, then you've not only found a conservation law, you found a conservation law that will be associated, that will be linked to this particular vector field, this particular invariance condition. And then you can go about reducing it, etc., and see if you can find solutions. So that's essentially what these calculations are about. And we show, in fact, that you end up with some rather nice, non-trivial conservation laws, which here will be a conserved vector of that type, and many other types, of course, just from establishing this relationship. So it seems to be moving in a way similar to what Noether's theorem intended, that if you take symmetries and conservation laws, you have a nicer way of finding these things. Of course, at that time when we did this, even though that's not very long ago, we didn't have powerful software. So this is all done by hand at the time. So David, we may need to relook at these things with software these days. Oh, I should comment on the fine work that David has done on applying these results. And I was feel very honored that David Mason has applied these results on some water for that is in mining and so on, to establish some sort of results for differential equations that arise there. This using this idea of symmetries and conservation laws. Okay, and then what we did was to extend this result to these differential equations I mentioned with small parameters. So you've got, for example, your wave equation, which gives you your full wave. You may want to perturb it with the first order, maybe damping term or something. So you've got your wave equation damped down to some sort of result at the end. So how do we deal with symmetries and conservation laws for that? Of course, this requires two things. One is you have to develop a whole notion of symmetries for these kind of equations. Then speak about what you mean by conservation laws for these kind of equations with these small parameters. And then see that you can establish some sort of theoretical results between these two notions analogously. So the notion of symmetries for these equations with small parameters was established by Ibrahimov's group, Baikov and Gazizov and so on. And they became quite famous for that in the Ufa group. The Ufa happened to be one of those cities in one of the states of Russia. Russia, yes, it's Russia. It's not the Soviet Union. It's still part of Russia. So that group was quite successful in developing this notion of symmetries of equations with small parameters. We then tried to extend this, and we found that the equivalent result for studying the relationship between symmetries and conservation laws for equations with small parameters happens to be this one. It looks very cumbersome, but if you look at the first equation there, that is exactly for the case when you don't have a small parameter, when your parameter is 0. And it turns out that for every higher order of the parameter, we have an additional equation. So this system then defines essentially the relationship between your vector fields, your invariance, and your conservation laws for equations with small parameters. I won't get into the details. I just thought I'd mention it here because it was one of the things we did almost immediately after our initial result in the previous slides. Okay, here's an example of that. Okay, so let me just speak about what a differential equation with a small parameter means. So you've got your basic KdV equation, there it is, right? Which represents maybe your waves in a shallow water situation. And then, of course, you're going to say perturb it with a small parameter, epsilon, this perturbation of the first order. And this term here could be any kind of a function that represents your perturbation. If it's, for example, a damping type thing, then you will have a UT term there. If you have a dispersion in the perturbed part, then your function f will be of the type ux or u XX, depending on the order of your dispersion. So that kind of thing. So equations of this type then are referred to as differential equations with small parameters. So you're looking at the invariance of that system, and then you would construct a conservation law in such a way that it experiences invariance or association with a vector field. Okay, and then these are just calculations that I won't bore you with all that. And this theory works quite well for situations like that. Now, I want to speak a little about partial Lagrangians. Now, to many people, initially, this seems like a very weird notion. So you look at a differential equation, which may or may not be derivable from a variation principle. So for example, maybe I'll write this like this. You might have your unique equation, right? That is not derivable from a variation principle. There's no Lagrange. You can't use Noether's theorem. There are symmetries, there are conservation laws, but these will not be constructed from Noether's theorem. You can study association via what I just mentioned earlier, using 2.1. So what we thought was the problematic term in this equation is the UT term. That's a part that will not give you the Lagrange. However, this part here, if you can find a function L for which your Euler operator, the thing that defines a variation principle. So you can find, if you can find a function L for which the Euler operator on that L gives you only this part of the term. And in a variational system, your Euler operator on your function L should give you the whole equation. But suppose it doesn't give you the whole equation. It gives you just part of the equation. So what we're going to call a partial Lagrangian. So here you have a function L, which is equivalently to the Lagrangian. Your Euler operator on there gives you part of the equation, and then the other part is not of Euler type. And the question was, can you use Noether's theorem some way to find conservation laws? And lo and behold, it actually worked quite well. So even in situations where the equation was partially variational, you could find a partial Lagrangian. You could go through a whole calculation similar to Noether's theorem by formula and construct conservation. There are some sort of things that, some sort of not very nice things that take place, but you can successfully construct your conservation. So here's an example of that type. So here I mentioned the heat equation. So you see, this is your function L, half ux squared. You do the Euler operator on that, it only gives you some part of the equation, the u double x part. The ut part is left out. But it turns out that if you go through the calculation, what you have then is your ut will equal to your Euler part, and the ut is of course isolated. And if you do the calculations using something very similar to Noether's theorem, you can eventually construct conservation laws in a way very similar to Noether's theorem. There's an extra term that Noether's theorem didn't account for. So I wanted to just build in that, and it comes in the proof of the theorem, which is quite nice. So there, that was the notion essentially of partial Lagrangian. So that was about 4 or 5 years after the initial. So these are then the methods up to that point that involved, that we worked on in finding conservation laws for various kinds of differential equations. Right. Enter George Blumen and Stephen Enko. Now, very recently, if you speak to anyone involved in this area, the result that is most quoted now, or the method that's most quoted now, is the method of what we call multipliers. So what they popularized was the following: that instead of finding a conservation law directly for your system, what you do is the following. You take your equation and multiply it by some unknown function and make the function dependent on your variables and sometimes even on the derivative of your dependent variable. So you're multiplying your function by some other function, which we're going to call a multiplier. It's very similar to what we do in the first order differential equations. We multiply by a variational factor, by a integration factor to make it exact. It's very similar to that. So you take a differential equation, multiply it by some factor, and then ask yourself, that does a product give you a conserved form? Very much like exact equations for first order, way back in your first year. It's exactly that question. And how do we proceed from there on? So you take your one part of your differential equation, say the left-hand side, multiply it by this factor unknown, which you're going to solve for. You do an Euler operator on that. So Euler Lagrange operator. And if you put that equal to 0, it turns out that that thing will then be conserved. It will be closed. And that's dependent on the following result. The result goes like this: that if your Euler operator on anything is 0, that thing is closed. And closed is conserved, conservation. Okay, so that is essentially what this result and the popularity of this result depends on. And you can do this by hand. You can find these so-called multipliers by hand. If the multipliers depend, say, on just your basic variables, your independent and dependent variables. No sooner you make them dependent on, say, derivatives, the calculations get very wild. But in theory, it can be done. And it turns out that if you take your multiplier and play around with it, increase the order, see how far you can go, either by hand or by some sort of software, and go further and further, you can end up classifying a whole lot of conservation laws which no Noether's theorem, which no previous method would be able to identify, simply because the method doesn't allow it. So if you were to equate Noether's theorem to this one, Noether's theorem will only pick up those conservation laws which gives you multipliers of first order derivatives, no more. This method you can have any order. You just have to have enough software to do that. So once you have the multipliers, then you have various options of finding your corresponding conservation. And each multiplier, each factor that you solve for will give you an independent conservation. Okay, very popular, and everyone in this area seems to be using or finding conservation laws will be using this method. So that was the one part of that history. And it's quite a well-established result. And it's very highly cited, that particular method, particular papers. Now, following that, here's an example of that type. So you take your differential equation multiplied by the Euler operator. So this is your Euler operator. You're solving for your multiplier. And once you've got the multipliers, you construct your corresponding conservation, either using the definition or some alternative. Now, here's a little bit of a history. I love conflict. So the conflict went like this. So Niall Dragimov, who died 3-4 years ago, I mean, who was on the staff at BITS for a number of years, and then he was on staff at the Northwest, developed a new approach to constructing conservation laws. And it went a bit like this. Oh, before I continue, I should say that these multipliers, they are always, it turns out, solutions of what we call the adjoint equation. So if you take your differential equation, for example, if you take your heat equation, right, and you do a fresh air derivative on it, right, you end up with an equation like this. So that is the adjoint equation. Now, solutions of the adjoint equation are always multipliers. So these multipliers there are always solutions of the corresponding adjoint equation. Now, let me speak a little about Ibrahimov's method. What Ibrahimov did was the following. He said, well, take the one side of your differential equation. When I say one side, for example, you have ut minus u double x. Let that be equal to L. He's now pretending that that is a Lagrangian of some other equation. It will turn out that that other equation will be much higher order. If I do an Euler-Lagrange operator on this thing, if I call that L, let's call this thing L. If I do an Euler-Lagrange on L, I'll get something probably fourth order. That's a really high order equation. And do an analysis on that higher order equation, right? I will end up eventually, this is what his method goes through. I'll end up with conservation laws for my original second order equation. And it will use the formula exactly like Noether's theorem. But Noether's theorem, of course, has to be extended to deal with higher order Lagrangians. And when you finally construct these conservation laws, you're essentially working with things like this that involves what is very similar to what Blumen and Enko regarded as multipliers. And here's the conflict. Enko and Blumen this was the conflict. They said that, well, this has been established already. That's what we've done in our multipliers. What Ibrahimov is doing is merely doing what was already done. But actually, there was something technically different, which I think sometimes when we have conflicts in results, we need to be careful. That maybe the result is not copied. Maybe the result is coincidentally copied. But sometimes there might be some technical difference which is not really, which shouldn't really be a conflict, but rather it should be something that maybe accommodates each other. And I think this is what I want to identify in the results that come here after. So just keep in mind, you've got the multiplier method of Enko and Blumen, and you've got the Ibrahimov's method, which takes a differential equation, assumes a multiplier on it, constructs a Lagrangian, goes in higher up in order, and then constructs a conservation law for lower down. It looks like the multipliers involved. And essentially, they are multipliers, but only these multipliers were not multipliers. He called them solutions of the adjoint equation. So the critics of Ibrahimov's method said, you're calling it what? Solutions of the adjoint equation. But our multipliers are solutions of the adjoint equation. So you're proving nothing new. So I always say that, especially for those of you who are always looking for conservation laws, and I'm hoping that someone in the distant audience do that too, that whenever you finally construct your conserved vector, always check whether in fact you have a non-trivial conserved vector. You know, if it turns out to be a constant, it's trivial. And sometimes these things look non-trivial, but when you do a total divergence of them, you get completely zero. You get things that are conserved under any circumstances. Those are trivial. You don't want to work with trivial conservation laws. So don't be too happy with a good result sometimes. Check the result. So it turns out that if you constructed the conservation laws using Ibragimov method, and then say, let's check. So you got your conserved vector. How do you check if it's a conservation law? You do a total divergence on them and see if you get your equations coming out nicely. And so in that spirit, I did the following. So yes, one of the examples. So this is an example taken straight from Ibragimov's paper that deals with this heat equation, ut minus u double x equal to 0. He assumes this one side of the differential equation, ut minus u double x, multiplies it by a possible solution of the adjoint equation. Here's the adjoint equation. Does an Euler-Lagrange operator on that? It's going to be fourth order. Opens the thing up and solves for these v's, which are going to be solutions, and then plug into Noether's theorem, Noether's similar to something like Noether's theorem, and construct the conservation law. And this is what he gets. But remember, he used symmetries. He used this notion of a multiplier, all put into one. It was quite neat, I think. But then let's just check what happens if you do a total divergence on it. This is where it can start getting a bit technical. I promised earlier that there'll be a bit of technicality at the end. So if you take your conserved vector, the components being t to the t and t to the x, the one representing conserved density, the other one conserved flux. And if you do a total divergence from that, now you may ask me eventually what's the difference between divergence and total divergence? But really that's going to be a talk of another time. But if you do a total divergence on that, do the calculations, and what you get is something that looks like this for this particular example. Now watch. You've got your adjoint equation there. Your multiplier is going to, your V is going to be eventually a solution of the adjoint equation. With the solution of the adjoint equation, this part will be 0. Not trivial. Then you've got the left-hand side of your original equation, your heat equation. Well, that part is equal to 0, but equal to 0 on your equation. So this too is equal to 0. Not 0 in general, but 0 modulo the heat equation. So what you got is 0 plus 0, which is 0, and then you've got your total divergence is 0. So you have a non-trivial conservation. All right, fine. That is merely checking. But it is what you get on the right-hand side before you set things equal to 0. What have you got? You've got your adjoint equation. You've got adjoint of your heat equation. You've got your heat equation itself, at least the one side of it. And look at the factors. Well, for those of you that are involved in symmetry, you'll find that this factor represents your characteristic of your symmetry that you've been working on. So your symmetry is built in there, right? This part, this factor is actually your symmetry acting on the function v. V happens to be that little multiplier, the thing that's going to be the solution of the adjoint equation. So you've got the symmetry coming there as a characteristic. You've got the symmetry that's coming there, your invariance coming there as acting on your multiplier. That's built in there. And each of these are multiplied to, in this case, your adjoint equation, in this case, your heat equation. The question is this always true? And it turns out, in fact, that we have a theorem here that says that if you were to construct conservation laws using Ibragimov's method, involving this symmetry, involving the adjoint equation, etc., you get conserved vectors for which, when you find that when you do the total divergence, you get this thing coming up. So you get your symmetry built in on the one side, you've got your adjoint equation, the symmetry again, and the heat equation. Different forms of the symmetry, of course. On this side, you've got the characteristic of symmetry. On this side, you've got your symmetry acting on a function, but it's there. One side, you're getting your adjoint equation, which you want, and then your equation itself, which you also want. Because you know, in the end, you want it to be non-trivial conserved vector. In other words, the total divergence must be 0. And I said, well, there's a number of examples of this type, and there's the theorem that says that if Z represents your invariance, your symmetry, if W is the characteristic of that, that's what I meant by characteristic. It comes from, you notice, your xi, your tau, and your phi are in the symmetry, and these are the very functions that are inside or in the characteristic function. So they sort of are synonymous. You've got a symmetry and its corresponding characteristic. And if you find the conserved vector using the Lagrangians method, which mimics Noether's theorem, this looks like Noether's theorem, right? And then you do a total divergence on that to check. You get exactly what I said. You get a characteristic, your adjoint equation, you get your symmetry acting on V in some way, and you get the equation itself, which will all disappear to zero non-trivially, i.e. on the solutions of your equation, so that you have a genuine non-trivial conservation law using the method of the Lagrangians. But it's got the notion of multipliers, it's got the notion of symmetry, it's got Noether's theorem, all nicely built in one together. It's really nice, right? And it gives you a non-trivial conservation law. So my question is that there's the end of the conflict. That if you look at the Lagrangians theorem slightly differently and say, well, it's using the notion of solutions of your adjoint equation. Why don't you take Blumen's method, find your multipliers, right? Those multipliers are going to be solutions of your adjoint equation, and then take it and impose it into the Lagrangians method. Problem solved. So you're taking two methods which are supposedly copying each other, but rather put it in together and you get this theorem. So you can identify your conservation laws or classify conservation laws, bring these two apparently copying methods into one. But actually, they're not really copying, they're actually supporting each other. So you look at finding your adjoint, or rather the solutions of adjoint equation, bring in the multiplier method, put it all together, and they work nicely, like one harmonious result. So that was what is built in this theorem. And when further to discuss other results relating to this notion of multipliers, symmetries, Noether's theorem, and see if we can construct decent conservation. If you got all this work, then you can start applying it on methods that was used by Petojo and Astri and so on. And that essentially is what I wanted to talk about. That last part I was trying to emphasize that sometimes when you have conflicting or results that you think were copied or conflicting and so on, you need to look a bit further and see how you can bring things together. They may actually be supporting each other. There might be things that you can actually put together and get better results out of it, like in this theory. So that's broadly, let me just summarize. I spoke about the history of constructing conservation laws when you may not have variation principles. And a number of people that worked on this in the past, and ultimately the popular method is this multiplier approach, and there were one or two others like the Lagrangians method, and these things all complement each other in the end. I want to speak about some of the references. So Stephen Enko and George Blumen had worked a lot in this area. I had the honor of working with both of them at some point. But the big result was in this and that paper there, in the European Journal of Applied Maths, and it's cited. I mean, really, almost enviably. Then I worked with Stephen Enko in extending these results to multipliers and symmetries and so on. He has a nice method that a long time ago spoke about constructing Lagrangians for particular kinds of partial differential equations. And I have to mention a history of Ian Anderson. Do I have time? Yeah, I must mention this. So initially, when Faisal and I looked at trying to generalize this result to partial differential equations, we didn't know about differential forms. So we submitted this paper, which was lots of calculations, but for a very restricted form for two independent variables. And somehow, this gentleman in Utah saw this result in this obscure journal. And he didn't send an email, he sent a letter, handwritten letter, to say, I looked at your paper and it looks interesting, but do you want to perhaps try this? And he stated the same thing using the language of differential forms. I don't know differential forms, but this thing looks really neat. Writing your conserved vector in a differential forms notation. You have to learn the whole thing about differential forms and so on. And lo and behold, the results, when you do it using method of differential forms, they just generalize completely to n independent variables. So in a sense, we are indebted to him. I hope I can meet you sometime. Chevyakov, also he was a postdoc with George Blumen, did a lot of work on writing software in Maple, constructing conservation laws, so on, using the method of Enko. Herman, I think we know Herman very well. Ames knows, he's visited Ames many times. He's visited WITS on a number of occasions. He's worked a lot again on conservation laws. He's worked a lot on writing various software and so on. He's worked with a number of people. He used to be the head of the School of Mathematics in the School of Mines in Colorado for a while. I'm not sure where he is now. And then, of course, they use the original results that Faith and I worked on some years ago. The last one being approximate symmetries, extending the results. And sadly, Gazanford, I heard, passed away last year. You know him. How surprising. Spent some time in his home when I visited his house. The classic Bible on the symmetries of differential equations due to Peter Olver in Minneapolis. There's another paper by Willie Herman. And I'd like to stop there. Any questions?
Can we thank the speaker first? Do we have any questions for Professor Kara? Anybody? Prof. Lubuma?
Thank you very much, Professor Kara, for a very talk. You indicated at the beginning the connection Lagrangian to know, is there any connection which can also be made, or are there work which have been done when you start with Hamiltonian instead of Lagrangian?
Right, good question. So there are many papers that are written equivalently through Hamiltonian system rather than Lagrangian. So you know that if you use your Legendre transformation, you can rewrite the system involving a Hamiltonian rather than a Lagrangian and vice versa. So yes, many people, in fact, again, I mean, some of the Russians were involved in that some years ago. And for one of our conferences, they presented these results. And yes, work has been done. But for some reason, it never caught on. I mean, the Hamiltonian picture is popular with people working specifically in Hamiltonian. So it was okay for them. But it never sort of had this effect of a general sort of interest. The Lagrangian one just took off. So it all works with Hamiltonians, but it just wasn't popular, unfortunately. And I would imagine it might actually be nice to work with Hamiltonians because you've got maybe a second order equation in your dynamical equation, which you write as a system of two first order equations involving a Hamiltonian. So it might be nicer to work. I don't know why it just never caught on.
Do we have any questions online?
No.
No, that's fine. If there's no questions, we could thank the speaker once more, and then that's it.
Thank you very much.